Okay, good morning everyone. We are only four students. It is very low number. I don't know the reason of this, but my grade is very low actually. Nearly my classes, half of my classes will be FF. Please say your friends. It's very bad condition for them. Okay, nearly we have a 70 student in this class, but now we are four students. It is very bad situation for me. Um yes, okay. Today we will start with the four advanced mechatronic system example actually. Maybe you know all of them probably, but they are my favorite mechatronic system design and approach. After that, we will continue with the some mechatronic system design process. Actually, it's like a social science. It's the engineering management side of the mechatronic system. Next week, we will start to the uh, next week we will start to the some mathematical explanation of the mechatronic engineering. Firstly, power electronics. After that, electric machine, signal system, and signal system and motor control. Part of the mechatronic system. After that, last week of the 4 or 5 weeks of the semester, we will continue with the robotic operating system, and then we will design a robot together and mechatronic system, or it's not a robot actually. Okay, now my first favorite mechatronic system, digital twin. You can see in the left side, left up side of your figure. This is very famous example. Maybe you know the metaverse. Metaverse is a very popular name, but it is not a metaverse. It's a classical digital twin. For example, you have a physical system of electric machine or turbine system. You will create nearly same with the physical system as a digital twin with your CAD or Analyze or etc. program. You can see all effect, all dynamic variation, all physical variation in your physical system you will see in your digital twin. This is very important part of the mechatronics engineering actually. Okay. Second one, I think autonomous vehicle. It's very popular. Another topic. You can see a man. He is sitting on the automobile and he watching a television or connect with your family, his family. So vehicle goes to fully self and autonomously. What's important for mechatronic system this vehicle? Because it is not just automotive engineering. It contains lots of electrical engineering parts, lots of electronics engineering parts, communication, etc. Third one, actually, is my uh, very oldest favorite, Mars Rover Curiosity. Actually, it duty finished, I suppose that. It's a Mars rover. It's very advanced mechatronic system example, nearly 20 years ago. They are contains camera, laser, energy management, solar panel, vehicle dynamics part, suspension, robotic arm, analyzer, very advanced communication protocols, etc. And lastly, you can see from television or YouTube videos, Boston Dynamics robot, humanoid robot actually, but it's not humanoid uh, because It's like a real robot because they have leg, they have arm, but they are programmable as their special duties. For example, sometimes soldier, sometimes farmer, sometimes runner, etc. They are very important for mechatronic example, I think. I hope end of your education or your master with master education, you will learn something about it. For example, in autonomous vehicle section, our university have all software and all hardware. If you want to autonomous vehicle engineer, please develop your skills to this direction. For example, sensor, software, vehicle dynamic, etc. Okay. If you want to learn digital twin, we have no course about it, but nearly all universities have no course because it's very new area for us. But you learn something about something from internet. Also, Curiosity and Boston Dynamics robot have classical electromechanical solution, arm, control, dynamic response, etc. Please aware of this subject in your class because every course will learn something about them to you. Now we will continue with the product creation process. This is the last class for this engineering management design. After that, we will build a mechatronic system step by step with the power electronics, with the signal system, with the machine, with etc. Now you can see standard timeline of a product creation. Maybe you remember from last week, we model. Maybe, oh, I gave you homework. I remember it now, but any student sent me any homework. Maybe it's my mistake. I don't know because I don't upload anything about it. But actually, don't wait from me any example. Actually, internet is a very big pool for find an example. But I will upload today. Okay, this is the first homework, so it's not important. But the next week, I am waiting your homework. I will upload explanation of it. Okay, we can continue. This is the standard timeline I said you, product creation process. Actually, it is closely related to the V model and is more directly suitable for planning purposes. The lower graph, you can see, shows us the yearly cost related to the effect of decision on the financial results of the project and emphasize the need to especially control the first phases. Now, you can, don't forget it, first 10 years of your engineering life will be passed with the design, hard handle operation, computer software, computer CAD drawing, also embedded system, etc. After 10 years, you will focus engineering management process with your all knowledge. Okay, this graph will be important in your engineering profession life. So after 10 years, you will attend lots of meetings, lots of committee. Teacher, we need an example. Okay, Ahmet, I will upload today. Okay. After 10 years, you will attend lots of meetings, lots of committee, lots of company visiting. First 10 years, you will work hard with circuit, with board, with software, etc. This is related with the second 10 years, this example, product creation. Maybe you have a company, you have a R&D department, you have a manager, etc. Now, this figure shows us, again I say, the time division of the product creation process, which is commonly used in industry. The phases 0, 1, and 2 correspond to the left leg of the V model, while the phases 3, 4, and 5 correspond to the right leg. You can remember from first course, the V model, we have a left side, we have a right side, or we have a left leg or right leg. From practical experience, it's known that many mistakes are made during the feasibility and definition phase when not sufficient time and effort is given to determine all factors that are at stake. If you want to design a mechatronic system, please aware of these steps. Please don't focus the result. Please think step by step. In this early phase, the decisions with often the largest impact on the success of a project are made at the lowest relative cost. If you don't aware of your next steps or next mistakes, etc., probably it will be very expensive design or over design. So starting off your design, please check all requirement. It is requirement analysis. Okay, what is my requirement? What is my electrical requirement, mechanical requirement? What is my success criteria? What is my aim, target, successful ratio? For example, my robot goes to 100 meter. What's the accuracy, error accuracy? For example, 0.01, 1%. Maximum 101 meter, minimum 99 meter. This is an criteria, error criteria. You need to define your successful criteria in the early stage of your project. Okay. Relation, actually, which relation? Cost and the successful relation is schematically shown in the second graph of the figure. You see, red line is the yearly cost of project, black line is the financial impact per decision. So, especially in this phase, the systems engineer needs to have a good overview on market demands and technological possibilities. Okay. In most cases, they closely cooperate with a product manager who take care of the marketing issues and represent the end user of product. This combination of often only two people is to a large extent responsible for the success or failure of your product. For example, one might say that a badly started production creation process can hardly be repaired, while of course a good start can still end up in a mess due to bad execution. This duo of the system engineer and product manager has to deal with the often contradictory requirements from the external market. They will define the final set of specified requirements in a process. Which process? Now, in next slide, you can see this process. This process shows us while the specified requirements are used as input for the development activities. Top down, you can analyze key drivers, operational drivers, roadmap, competition, regulation, ideal reference design, prototyping simulation, bottom up, existing system. After analysis of these criteria, you will see specified requirements. We can say for this criteria boundary condition. And a mechatronics engineer can easily add all kinds of boundary condition and take precaution for all imaginable risk in functionality without sufficient awareness of incurring cost when not sufficiently critical. Designer just use these requirements and create an overkill in functionality. As a mechatronics engineering, your main target, you will analyze the all specified requirement. At we can start. Okay. What is the budget? In your screen, you see an accuracy budget of positioning system. It is just an example. It indicating how the top-down user requirements are divided over the different layers of subsystem with their corresponding source of errors. It's clear that a systems engineer who has to define these user requirements needs to have a true insight in all subsystem that contribute to the overall and result in order to give the largest error budget to the most critical subsystem. The mechatronic engineer also has to decide which part of the budget is allowed to the smaller, frequently occurring random error sources. This is noted in the item other in your figure. This process of budgeting of user requirement is only one half of the total activity, as the top-down process to divide the requirements is followed by bottom-up process to determine the corresponding specified requirements. In this way, the expertise of the responsible subsystem designer is used to create a balanced requirement budget without over specification. In your screen, sensors, actuation, drive, guiding, tolerance, stability, others, bearing, ball, and grooves. For example, the first stage, overall. It's an overall looking up. Overall system builds from sensors and actuation. Now, maybe you don't know what's the sensor, what's the actuation, etc. Actuation divide up the three parts, actually two parts, guiding and drive. Guiding three parts, bearing, tolerance, and stability. And bearing divide up two parts, balls and grooves. This is the typical budgeting approach. Now you can see actually this is the natural flow of the product development. In the figure you can see a graphical way that the process of developing products takes place in a continuous flow of changing external influences. The increasing demands of the market, together with the also increasing technological developments. For example, it's a good example we have here. A good example is the development of the personal computer, Initially, the combination of IBM company, Intel, and Microsoft could determine their market approach without the need to take the competition into account, However, at some moment in a time, remember, the competition like Apple and the Linux community had arisen, forcing the seemingly monopolistic PC competition league to listen to their customers. It's a good example for competition and road mapping of product development. As a consequence of this competitive environment, for example, IBM, Microsoft versus Apple and Linux, for example. Marketing research is needed to get a good feeling to the market dynamics and base the design decisions on reliable estimates of the future customer needs and technological opportunities. We can say to this approach, road mapping. You can see in your screen a very easy roadmap and basic roadmap. It's just a lecture example actually. It is indicating the different engine drive principles that were expected to be developed by the car industry. Product range, one of them turbo type automobile. Product range, one of them hybrid, one of them electrical. This is the roadmap. First 2 years product range as a turbo type vehicle, and next section hybrid and electric vehicle. Actually, today we can say for this example it's very early consideration. Now we are hybrid stage. It's the very early estimation. Innovation driver section, we can see kilometer hour, fuel consumption, and acceleration. This example probably from United States because 10 liter per kilometer is very high. And maximum speed and acceleration 9, 8. Yes, it's just an estimation from a company or just an example. Actually, numbers is randomly assigned. Also, technologies improved turbo B, hybrid technology, and all electric vehicles. And the last section of the figure, time diagram. Enhanced turbo development,
2 years, and hybrid studies start the half of the second years, and the full electrical drive study start with the quarter of the second years to the last years. Actually, this is planned activities. This is the time diagram. Okay, last section of our introduction to system design methodology. Here you can see concurrent engineering results in shorter lead times by working in parallel on different phases of the project. It is a diagram, serial engineering or parallel engineering. You need to know all charts for design a timeline. Firstly, you will define your work package. What is work package here? Product definition, concept design, and detailed design and log lead item order and delivery, integration and test, and production. This is your work package. First work package, product definition, last work package, production. T0 time, T0 it defines the starting of the project. T0 is equal starting date. Here we have 4 years in this project, example project. Serial engineering approach, if you complete the first work package, after that you can start the second package. In parallel engineering, all work package goes with as a parallel, you can see. For example, product define, finish at the half of the 13, but the concept design is not waiting the finishing of the product design. It starts second quarter of the 13. Okay. As the classical engineering design approach, now we can start next section of the course. I will share another part of the course. Yes. In mechatronic system, especially, we need some important disciplines. One of them, power electronics. One of them, electric machines. One of them, signals and systems. One of them, communication and electronic circuit design. Actually, we can say something about the mechanical design, but in our course, generally we will focus electronic design and software design. So maybe another course you will learn mechanical topics of the mechatronic systems, but this is not a mechanical focused course.
Okay, maybe you hear from your friends, your past, your high school, etc. What is the power electronics? Why do we care? Okay, now think about your daily activities. Which of these are driven by a plug or an energy source like a battery? We don't only utilize power, but we rely on it. Take, for example, your morning routine. Okay, you turn off your alarm clock, you turn on the lights in your room, perhaps you use an electric toothbrush and pour yourself a cup of coffee or tea, and then you check the email on your iPhone or Android phone. You have used more than half a dozen power devices before you even leave for work or university. Even the automobile that you drive to work in has a combustion engine, but this automobile is littered with electronics. So, why do we care? Why do we care about the power electronics? None of these devices work with a dead battery or a plug that is pulled. All of these must have power. So, what exactly is power electronics? Well, electrical power is measured in watts and is calculated as the product of instantaneous current and instantaneous voltage. Energy, on the other hand, is the product of power over a period of time and is measured in watt hours. In your all professional life, please aware of these differences. Power and energy are different topics. Okay, one of them kilowatt or watt, one of them watt or kilowatt hour. Okay, every home is connected to utility grid. Utility companies bill business, schools, and residents for electricity and charge by the kilowatt hour. Typical energy prices are in the range of, let's say, for example, $0.1 per kilowatt hour. So, where is power electronics used in our mechatronic system in our life? Probably you know some part of the which components are power electronics in your robotic systems, but please imagine it. In your robotic system, nearly all electromechanical needs, electric machine, servo motor driver, you can imagine drone motor controller, battery controller, also main control board, power needs. For example, you can image robotic arm. Starting from your arm, you have one motor in your finger. Every connection part needs a finger, needs a motor. Every motor needs a power electronic circuit. Every power electronic circuit needs a microcontroller and communication. Every microcontroller needs a software. We can call this process generally power electronics. So, where is power electronics used? Okay, we have discussed one slide ago. We have discussed what power is and why is important. Let's say now discuss where you can find it in your Mars rover, in your autonomous vehicle, in your digital twin, in your autonomous. What's the last example? Yes, Boston Dynamics robots. We are needing battery energy. Okay. To be more specific than just everywhere, power is used to support the work of loads. Electric motors, like in a vacuum cleaner or electric car, require appreciate voltage and currents to operate. For example, you can imagine home theater speakers receive power over speaker wire that is sent by a receiver. Microcontrollers are common in embedded application. They support the activities of washing machine, microwave oven, and function in automobiles. Okay, what is the we defined what is the electric motors, speakers, microcontrollers. Now FPGA. What's the FPGA? Probably you will use lots of time. FPGA are becoming more frequent in data centers due to the performance per watt advantage versus other technology. They are used to accelerate high performance computationally intensive tasks like those performed by search engine. On the other side, DSP, digital signal processor. DSPs perform signal processing, audio video comparison, speech comparison, and a wide array of other process. Microcontrollers, FPGA, and DSPs alike are powered by low voltage power supplies. This is the heart of your mechatronic system, microcontroller, DSP, or FPGA. All processes are managed by microcontroller, FPGA, or DSP. In most cases, our microcontroller or FPGA work with the 5 volt or 3.3 volt and range from the power levels of microwatts to hundreds of watts. Power is also used in displays to drive backlight LEDs in computers and televisions. Now we have discussed where power is used, so now we need to answer the question of how do we get it? Actually, all students know the power generation. Something we need to say some things about it. Power is not readily available like water on a stream. Electricity must be generated from an energy source, also known as primary energy. Our world is filled with the primary energy, which is an energy form found in the nature, that has not been subjected to a conversion or transformation process. Primary energy can be classified into two categories, renewable energy or non-renewable energy. Non-renewable energy sources include fossil fuels like coal, oil, and natural gas. and are not easily replaced. However, renewable energy, on the other hand, are more easily replaced. Common examples are wind, sun, and flowing water. But an important question remains: how is an energy source converted into electrical energy? Well, this process varies for different types of source. Perhaps the easiest to consider is the non-renewable fuels. Inside the power plant, the fuels are burned and heat exhaust is created. This heat exhaust is used to boil water and create steam. Then the thermal energy of steam is converted into mechanical energy by turning a turbine. The turbine is linked to a generator that spins around with turbine. This is the classical process. As we discussed on the earlier slide, a power plant creates electricity from an energy source. Next step, deliver the energy. Here, power electronics role is important. Why? The process is to deliver the energy in the form of electricity to the consumer in homes, schools, and business. Power distribution, as this is commonly referred to, is accomplished on micro level through what's known as the grid. The grid is complex interconnection you see in your screen. Actually, this is not important for us, distribution lines. Because of power loss, we are using a AC distribution line. But here, important parts for us, power electronics section, power distribution on the micro level leverage many of the same techniques. This is the typical block diagram of main controller. For example, this is a robot controller. This is the electronic circuit boards of heart of your robot. What's the important here? Now, the power source to the controller is 230 volts AC. But we don't use it. The AC voltage firstly is converted to 12 volt DC through a power converter. This is your first power electronic circuit, which we can treat like a black box for now. The 12 volt bus voltage, as we call it, is transmitted across the entire all motherboard. This is just a charger or power supply, you know. After scattered bugs, the top and the bottom sides of the main boards are different loads that combine to form the overall system. These loads, as shown, include fans, memory banks, system input-output rails, CPU, just to name a few. All parts of the motherboard working in different voltage level: 12, 3.3, 0.9, 1.5. But the hour supply or battery, firstly 230 volt AC or 12 volt. We need to design power electronic circuits for adjust the voltage level. To summarize, power source in your schools, homes, university can include AC outlets, okay, which we saw on the this figure, batteries,
wall adapters, laboratory sub-equipment, generators or PC USB ports, just to name a few. Power can then be converted in the form of an AC to DC conversion, DC to DC conversion, or a black box like a wall adapter. This converted power is then used to support the activity of all types of electrical loads. So, in briefly, we can say as a lastly about the power electronics, power source we have, power conversion section, and load. Okay, after this week, we will continue with the what's the inductor, all elements, etc. For today, it's enough, I think. Next week, we can continue with the passive elements of the power electronics. After that, we will continue with the converters. Okay. Thank you for your attendance. Next week on Monday, we will start at 10 o'clock again. From 10 o'clock to the 12 o'clock, our course time. Some weeks we have a 1 hour, some weeks one have a 2 hour course. I will upload your first homework 10 o'clock, Abdul Bari. 10 o'clock every week. We will start 10 o'clock from 10 to 11 or 12. Some weeks 2 o'clock, 2 hours, some week 1 hour. 1 hour. Okay. Thank you. See you later. Bye bye.